What's up? Sorry, that's my little catchphrase. Back with another LeetCode Path to Pro video. It is Monday, May 1st. I got an offer for data engineering internship. Pretty hyped. Probably gonna accept. Yeah, there seems like a cool company. Met with the manager. Manager seems super nice. So, I'm stoked. Yep, that's a little update. Um, you know, it's like I said, it's May, so I don't start at Georgia Tech until probably early August. So got a few months, but yeah, let's get to this problem. So if you remember, I did maximum depth. Today we're gonna do minimum depth of binary tree. So it should be pretty much the same. So first, I'm going to show the iterative solution. And if you're curious what depth is talking about, we're talking about so if there's just a single node, so like this is a node, this is our binary tree, if these are null, like there's no leaf nodes. It's just that this is a depth of 1. But then, if we make one of these nulls into an actual node, give it a value, then we now has a depth of 2. Add another, depth of 3, and so on. Yeah. So if you remember, I solved this yesterday recursively with a depth first search. So we're going to do that again. So if not root, and it's really, I'm thinking it's going to be the same exact thing. Return 1 plus min plus min of self dot min depth. We're just making a recursive call on the root. I always do that. That's like a weird thing I do. I always type slef. Root. And that should. Might be missing something. Maximum recursion depth. See? Let's see. Let's look at the answer from yesterday. I think it's the same. This is what the other page. As you can see, I'm hitting all the easies. Oh, this is a medium. Oh no, this is an easy. Other root dot left. Yeah, so you have to tell it. Is that what? You have to tell it to go left and right. But I'm thinking this will be the same. Wrong answer. Ooh, interesting. Wait, given a finite minimum depth is the number of nodes along the shortest path. What is this example? It's going to be 2. Null. 3. Null. 4. Null. 5. Yeah, so that's, why is it, interesting. And I'm outputting 1. Because you can't just return the minimum. Yeah, because right, in this case, there is no... Oh, down to the nearest leaf node. So we do need to hit a leaf node. Ooh, this is a more interesting problem than I thought. Okay, cool. So this still stays, but we can't just recursively call. We want to say, so we're going to say while root or yeah, you know, if we've got left is using null, it's a none. Right, because if we ever hit a node, could we just leave it? Man. I'm sure there's a way to like check to make sure that we left. And I want to look up solutions. Let's just try to write. So like, if your dot left, none. This. I'm curious if this will work. Else if right. Well, we still want to do the min. Or, do we? I wonder if this would work. Is it equals equals? I wonder if you have to put the minimum. Minimum. Interesting. How can we do this? So let's use that example. I mean, I think, let's get this back. I feel like we can edit this statement. So, door just. It's too late. So yeah, this doesn't work on the second test case. We're gonna get bumped. I mean, we don't want to return the max again. Oh, wait. That works for that one. So like, do while node. Right. Else. So let's check and see, like we have both, and then else if no dot left. How would we say if no dot right is missing? F dot val? Def. And here, this statement again. Oh. Right. I don't think I'm doing this right. But yeah, after this, let's look at some solutions and see if we can figure out. Yeah. Wait, do we just do no dot val? Yeah. I'm a little stumped. Let's see. Easy to understand, you say? Well, that's really smart. So here he's setting variables, or she is setting variables, and they're calculating the minimum depth of the root dot left and root dot right, or the depth, and they're saying, okay, return left plus right plus 1 if left is 0. So in this case, right left is 0. Or, you know, there could be another case where this is just on the left side and the right is 0. Else, we're taking the minimum of the left and the right. Yeah, that's really smart. So that's, I originally was like, okay, this problem's already solved, like, from yesterday. Like, I'll try to do the iterative solution. If root is none, try to zoom out. This is doing the same thing. I wonder if there's anything. If not, no doubt. So that's the correct way to say. Weird. So doing kind of in a weird way here. But yeah, this answer makes a lot of sense. So right, they're saying if not root, return 0. And they're saying variable. Okay, we're going to find the depth of over here, the left. Well, that's 0. Then we're going to find the depth of the right over here, and it's, well, it's 0. And from the right over here, it's 1, 2, 3, 3. And then we're going to return left plus right plus 1 if left equals 0 or right equals 0. So in this case, left equals 0, so we'll return 3 plus 1 is 4. Depth is 4. Else, we're taking the minimum. So let's just say it's this. There's a node here. Oh, I can get rid of all this actually. Super easy. So let's say there's a node here. So here, the depth over here is 1. Depth over here is 3. So then we'll return the min of left and right plus 1. So it's 1 plus 1 equals 2, which would be the right answer in that case. Cool. That's a really good answer. I like this solution a lot. Shout out whoever came up with that. And it looks like it's kind of quick. Memory should be O of h, where h is the height of the tree. And the time complexity should just be, I think, O of n, because we're going to go through every node in the tree. Yeah, I think I already submitted it. Yeah. Alright, cool, y'all. Thanks for watching. Peace.